Hi everybody, welcome back to the section 3.1 video. In this video, we're going to take a look at another differential equation as a mathematical model, and that's going to be Newton's law of cooling and heating. Okay, so let's take a look at the initial value problem that we've developed previously in section 1.3. But once again, we have the tools now to solve this and be able to investigate it a bit. So here's an initial value problem. Here's the model. D over dt equals k times t minus t sub m. And of course, we have an initial condition at time 0. We have an initial temperature T naught. So let's go ahead and break that down. Some of the things we just said. K is a constant of proportionality, a proportional constant. T sub m is a constant or ambient temperature. So like the temperature in the room. And T sub naught is the initial temperature of the object. Okay, so once again, we were able to develop a model and the differential equation above based on the statement back in section 3.1. Okay, but now we have the tools to actually solve this and get a general solution for the famous Newton's law of cooling and heating. So let's go ahead and solve that. So here we have the differential equation dt over dt. The capital T is for temperature, lowercase t is for time, equals k times t minus t sub m. Okay, so what type of equation is this? This is a separable differential equation. So I can move some terms over and isolate the variables. So what we're going to do is switch these up a bit. And what we're going to have is divide by t minus t sub m over to the left. And we're going to multiply by dt on the right-hand side. So this would be k times dt. And it's a separable differential equation, and we can go ahead and integrate now. So what we would end up with is natural log of t minus t sub m equals kt plus c, because k is just a constant, so it just picks up a, a variable t. And once again, if we have natural log, we want to base e to both sides. That will cancel out the natural log, and I'm left with the absolute value can go away. T minus t sub m, e to the kt plus c. And using properties of exponents, the e to the kt plus c could break those apart, get just e to the c. And we typically don't want to have e to the c. That's just a constant. We can make e to the c equal to a constant a. So we can have t minus t sub m. Going to bring that a up in front, but e to the kt. And let's go ahead and add our ambient temperature T sub m to both sides. We'll get T equals e to the kt plus T sub m. Okay, so that is our solution, but we're not done yet. We still have this initial value to use to fill out the rest of our solution to Newton's law. So we're going to use our initial condition. At time 0, we have an initial temperature. And so T naught, going to plug that into our solution, A e to the k times 0 plus T sub m. So T naught equals A e to the 0 plus T sub m. E to the 0 is just 1. So T naught equals A plus T sub M. And so we can say A, if we move the T sub M over to the left-hand side, is T naught minus T sub M, our ambient temperature. So we're going to take this, plug it back into our original equation, and have the solution. Therefore, the solution is always going to be of this form. T sub naught minus T sub M, our initial temperature minus our constant temperature, e to the kT plus our constant or ambient temperature. So this will always be the solution. Okay, so we can take the solution, we can always use it in Newton's law of cooling and heating problems based on what the question is giving us, but we can always use this solution. Okay, so we're going to use this in the next example, but that's it for this video, and I'll see you in the next one. Okay, take care.